Hello everybody, my name is Aaron Barrera, and I am an applications engineer for brushless DC motor drivers at Texas Instruments. Today, I would like to discuss how motor drivers are used inside of engine control units in 12-volt and 24-volt automotive systems, and how Texas Instruments motor driver solutions can be implemented to drive engine loads. In this video, we'll go over how internal combustion engines work, the purpose of engine control units, or ECUs, the type of outputs to drive in an engine, and TI motor driver solutions to drive these outputs. To understand the importance of an engine control unit in an engine platform, let's review how an internal combustion engine works. An internal combustion engine, known as an ICE, is a heat engine in which the combustion of fuel generates force to do work. At the heart of the engine are the crankshaft, cylinders, and pistons, which fire off in a pattern to convert linear motion into rotary motion of the crankshaft. Many other components such as intake and exhaust valves, camshafts, and the timing belt are used to increase the engine efficiency. All of these parts are structured inside the engine block and cylinder head. These structures not only protect the engine, but also allow it to dissipate heat generated from friction to the atmosphere and engine coolant. To combust fuel into usable energy to do work, a four-stroke process is used to produce power. The first stroke is the intake stroke. In this step, the intake valve opens to allow air and fuel to mix in the combustion chamber while the piston moves downwards in the chamber. The second stroke is the compression stroke. The piston moves upwards to compress the air-fuel mixture and add force to the combustion. The third stroke is the combustion stroke. The spark plug ignites the air-fuel mixture to begin the combustion reaction. The force generated from the reaction forces the piston to move downward. Finally, the last step is the exhaust stroke. The exhaust valve opens as the piston moves upward to let out the burned air-fuel mixture. In succession, these four strokes are responsible for creating the power needed to spin the crankshaft and drive shaft, which makes the wheel spin and the car move. Most cars have a four-cylinder inline configuration, one cylinder for each stage of the combustion cycle, timed to fire off at different strokes in the process. Some cars can have 6 or even up to 12 cylinders for added power. The goals of internal combustion engine design are to increase fuel economy and efficiency, minimizing size and cost, and adhering to fuel emission standards. To achieve a rated fuel economy, the engine must efficiently output power to move the car by ensuring there are minimal losses in the system. Sensors are prevalent in the engine design to provide closed-loop feedback. Furthermore, a trend this decade will be direct fuel injection into the combustion chamber rather than at multiple points in the intake manifold to make vehicles more efficient. To reduce the size of ICEs, the trend to electrifying powertrain systems is increasing as the automotive industry continues to transition towards hybrid electric vehicles throughout the decade. Increasing the number of electrical components can heavily reduce the size of the engine. Although more expensive to implement today in powertrain design due to the cost of efficient power semiconductors, HEVs and EVs will continue to grow in demand and diminish in size and cost. More importantly, many major automotive countries in the world are enforcing stricter standards to reduce emissions and pollutants from automobiles. The United States, Europe, and China all have their own regulated standards that challenge automotive manufacturers to produce cleaner cars. To meet these goals, performance and management of the engine must be continuously monitored. This is referred to as the Engine Management System, or EMS. The Engine Management System is a closed-loop feedback system that monitors engine performance through a control unit, outputs loads to adjust performance, and sensors that feed back into the control unit to calculate its new performance. We will go into each aspect more in depth throughout the video. In taking a closer look at a typical engine management system platform, there are a myriad of sensors and outputs. Outputs are anything that can be controlled by a driver, and inputs are any sensor that can measure the parameter of interest and convert it into an electric signal. There are as many as 60 high-side, low-side driver outputs and 8 injector drivers to control in an EMS. To control engine outputs, we need to use an engine control unit, or ECU. An ECU is a special automotive CPU that takes input data from all sensors in the engine system, compares the current performance data to lookup tables, processes the data to make calculations, and energizes output loads to control processes in the engine platform. By using sensors for feedback, it creates a closed-loop system that significantly increases the efficiency of the engine. Let's take a look at how everything falls in a reference diagram for this end equipment. A variety of input sensors are used to manage the performance of the engine when it is running. Parameters like temperature, pressure, position, exhaust, torque, and current must be monitored using dedicated sensors. These sensors send electrical signals to the ECU that can calculate its current performance versus its ideal performance. This is done by comparing the current performance values to internal lookup tables in the ECU to determine the adjustments needed in the system. Finally, to adjust to the ideal performance, the ECU sends signals to the outputs in the system to control the parameters needed. We will discuss these in detail later. In addition, solenoids can be driven with different configurations, with each configuration offering its own trade-offs. Low and high side drivers use an N-type MOSFET and freewheeling diode in their topologies. To turn on the driver, simply turn on the FET with the gate drive signal to dissipate current through the solenoid from VM to ground. Both drivers require a freewheeling diode in parallel with the solenoid so current can be recirculated if the NMOS is switched off. In addition, when using a high side or low side driver with VDS monitoring, the gate driver IC can only detect either a short to battery or ground, but not both. The push-pull driver uses a half-bridge configuration where the solenoid is connected to the shared node between the MOSFETs and VM or ground. When one FET is turned on, the opposite FET is turned off to allow current to dissipate through the solenoid. When the on FET is turned off, then current can be recirculated back to VM or ground through the opposite FET rather than using a freewheeling diode. The gate driver IC can detect both shorts to battery or ground, but also could introduce sneak paths through the gate driver IC that could unintentionally energize solenoids. For more information, please visit the Using DRV to Drive Solenoids application note from Texas Instruments. In the next few slides, we will cover in depth many of the engine output loads you can find in a typical gasoline or diesel engine platform. The first engine load we'll cover is electronic throttle control, or ETC. ETC adjusts the amount of air allowed into an automobile's combustion chamber based on the position of the gas pedal from a position sensor. The position of the gas pedal is detected by a position sensor and sent to the ECU. The ECU then calculates from that position information how to drive a DC motor, which opens or closes the throttle valve to control how much air is allowed into the combustion chamber. Finally, a throttle position sensor is used to close the loop and sends feedback to the ECU to improve more accurate engine performance. An H-bridge configuration is used for the DC motor to control direction and braking. The fuel pump relay is the primary electronic switch that controls power to the fuel pump. It is an electromagnetic switch located in the fuse box behind the engine bay that powers the pump when a logic level signal is sent from the ECU. This can be controlled by a single high side or low side driver. The exhaust gas recirculation valve, or EGR valve, is used to recirculate exhaust gases into fresh intake air to lower the combustion temperature in combustion chambers. This help reduces the amount of nitrogen oxides, or NOx, and prevents premature detonation of the air-fuel mixture in the combustion stroke. The valve is controlled using a stepper motor, brush DC motor, or solenoid. A temperature sensor measures the temperature of the intake manifold, and a signal comes from the ECU to control the opening of the EGR valve. A wastegate valve limits exhaust gases going through the turbocharger and bypasses them directly into the exhaust. This helps maximize the boost pressure of the turbocharger without overpressurizing the engine or turbo. This bypass protects the turbocharger from failure, which reduces fuel consumption and reduces CO2 emissions. The wastegate valve is conventionally driven by a solenoid, but can be motorized using a butterfly valve design with a DC motor. Therefore, a high side or low side driver, or H-bridge, can be used for the wastegate. Idle air control, or IAC, is used to control the amount of air that is bypassed into the fuel injection system from the throttle plate. This is needed when the engine is idle, or the amount of power the engine needs to work without moving the vehicle. An IAC valve can be motorized with a stepper motor or be solenoid driven, depending on the amount of control needed. The amount of air needed to keep the engine idle can depend on a multitude of sensor inputs. An oxygen heater driver is used to drive the heater inside oxygen sensors found before and after the catalytic converter. In order to measure oxygen level of exhausts, the sensors need to be heated to operating temperature in order to get an effective analog voltage reading. The heater is a resistive load that is typically driven with a low side driver. The heater has its own connections labeled battery and heater, or HT plus and HT minus, in the 4-wire pinout of the sensor. There is conventionally a bank of sensors before the catalytic converter, but there can be a second bank after the converter to measure the oxygen in the exhaust after the oxidation process. A canister purge valve prevents fuel vapors in the fuel tank from escaping into the atmosphere. Fuel vapors are purged from the charcoal canister into the intake manifold and burned inside the engine when the valve is open. These are typically solenoids that could be driven by a single high side or low side driver. The starter relay actuates the starter motor. The positive of the battery is connected to both the starter motor and starter relay. When keys are turned into the ignition, it closes the connection and sends current into the starter relay, which then closes the connection to send current into the starter motor. The starter motor then spins the crankshaft to begin moving the pistons until the combustion process takes over and turns over the engine. The starter relay is the engine load that draws the most current from the battery, up to 10 amps depending on battery voltage and size. This can be powered with one high side or low side driver. A malfunction indicator lamp, or MIL, otherwise known as a check engine light, is a 12-volt incandescent mini bulb that lights up on a dashboard when there is an engine malfunction. An engine malfunction can be an error signal from the MCU if feedback from a sensor indicates that a system or part is not meeting specifications or working correctly. To turn on this 12-volt load, a high side or low side driver can be used. All of the loads discussed previously can be fired off hundreds of times per second to maintain engine efficiency and performance. A driver solution should be able to address all of the following issues. Have a wide input range rated for 12 volt, 24 volt, and emerging 48 volt automotive systems. Be capable of driving multiple loads independently and simultaneously. Have protection and diagnostic features to detect any shorts or faults, and be easy to implement and use in a design. TI offers motor driver solutions that address all of the previously discussed issues. There are two families of automotive-grade TI motor driver solutions that have independent half-bridge or MOSFET modes to drive engine loads independently. The DRV 8340Q1 and 8343Q1 are automotive gate drive units with 3 independent half bridges rated up to 60 volts max. They are versatile parts that can control a variety of load configurations, including up to 6 high side or low side solenoid loads using independent MOSFET mode. The gate drivers have dedicated source and drain pins to monitor and protect the system in the case of fault conditions. The DRV 8343Q1 includes 3 integrated current shunt amplifiers that can measure motor phase currents through a low side shunt resistor. Current can be regulated by adjusting the duty cycle of the input control signals. The DRV 887X-Q1 family of H-bridge motor drivers have integrated FETs, current sensing, and integrated current regulation. All of the devices in the family can drive 2 independent solenoid loads using independent half-bridge mode and can tolerate a wide supply voltage range of 4.5 volts to 37 volts. The DRV 8876, 8874, and 8873Q1 have varying specifications for peak current and total RDS on to support a wide range of inductive load currents. All solutions on this page are AEC Q100 qualified and are temperature grade 1 from -40 to 125 degrees Celsius max ambient. Let's go through an example of using a high side and low side driver to efficiently drive a solenoid using the DRV 8343Q1. A high side plus low side configuration is used because it actuates the load while protecting it from many dangerous overcurrent faults. To generate the voltage needed to move the solenoid position, a higher duty cycle is used to simultaneously turn on the high and low side FETs. This yields a larger amount of current that will dissipate as heat in the solenoid winding. Reducing the PWM duty cycle after the load turns on will lessen the amount of current dissipating through the solenoid while it is still energized. This will lower the thermals of the solenoid and increase its longevity, especially when running multiple solenoids in parallel. When the FETs are switched off, current recirculates through the freewheeling diode and solenoid, preventing large amounts of current flowing into the IC through the SHX and DLX pins. Suppose a short to ground or battery is introduced, sending a dangerous amount of current through the FET. The DRV 8343Q1 can monitor the VDS voltage of the high side and low side FETs so that if it exceeds a preset threshold, a comparator will trip to shut down the gate driver IC and external FETs before getting damaged. By using a high side and low side driver, the system can be protected from overcurrent conditions with proper configuration and design. Another TI solution is TIDA 060030, which is an automotive 12-volt to 24-volt engine load interface reference design targeted for engine control units. This feature design uses the DRV 8343Q1 as mentioned on the previous slide, along with an MCU to drive engine loads found in ECUs using 4 different load configurations. The configurations implemented in the design are a low side driver, high side driver, a combined high side and low side driver, and a push-pull driver. All configurations are driven using the DRV 8343Q1 independent MOSFET mode and can be used for solenoids, relays, actuators, and brush DC motors. The design also supports short to ground and battery diagnostics, protection features, and fault reporting from each output configuration. Additionally, TIDA 060030 is rated for up to 60 volts, 20 amps max, is automotive qualified, and is rated for temperature grade 1 from -40 to 125 degrees Celsius. The solution size is small and is easy to implement for any type of engine load found in 12-volt and 24-volt automotive systems. For more information on TIDA 060030, please visit ti.com/tool/TIDA-060030 to download the design guide and design files. So in this video, we've covered a lot on how an engine works, what an engine control unit is, why motor drivers are important in engine controller design, and what solutions TI has available for driving engine loads. To conclude, driving a gasoline or diesel engine does not have to be complex. Engines may be complex in mechanical design and operation, but electrically, TI is working on mitigating those challenges to make engine controller design simple and efficient. There are an abundance of driver outputs in a gasoline or diesel engine management system. At the heart of these loads are solenoids, relays, DC motors, or stepper motors, which are controlled by the ECU to maintain engine performance while reducing emissions. Engine control can be as straightforward as using a high side or low side driver to actuate the load, or can use more complex configurations for added protection and diagnostics. Many TI automotive solutions and resources exist to enhance and simplify engine controller design. Visit ti.com/motordrivers to find devices, reference designs, app notes, and learn more. Thank you everyone for watching this video.